Good. All right. So let's get started. Today is lecture 3020, and we're going to talk about the scope of thermodynamics. And one last note, I'm in another location, so getting used to the configuration here with the camera. My face is hidden behind the camera half the time. I'm sorry for that. I think that by Monday I'm going to have this all worked out, but at least you can see me. So there we go. All right. So what does thermodynamics treat, and what does it not? That's the topic of the day, the scope of thermodynamics. So first, we're going to talk about states of matter. Right, what is a state of matter? There's different ways to define it, of course, but we're going to define it as something that has well-defined responses to, let's say, squeezing, heating, adding more of the same, stuff, and adding different stuff. And we're using colloquial language here, but the way that matter responds to stimuli like these is characterized by response functions. And we're going to write these down. So these are the types of things that we're going to do throughout the term. Another thing that we often do to states of matter is we apply fields. We don't treat that in 020, we don't get there. But the types of fields we might apply are strain fields, gravitational fields, magnetic fields, or electric fields. We might just get to a little bit of electrochemistry in the class. We'll see if we get there. But otherwise, we're not really going to spend time talking about applying fields. So we have this stuff, and we're characterizing it, and we characterize it by how it responds. Okay, so that's one thing that thermodynamics treats. Thermodynamics also treats transformations between states. So this is pretty generic. We have some state A, and it transforms to some state B. Okay. It treats transformations. So we have starting and final states described certainly. So we have certainty over what those states are, how they behave. Phase diagrams are really useful for that. Right? You say, here's the state that you expect. Let's change the temperature or pressure. Here's the final state that you expect. So, we can use phase diagrams to make these predictions with certainty. One thing that's annoying about thermo when you first learn it is that the process is abstract. Meaning, thermo tells you how things start out and how they end up. But a process of transformation is very much a black box in thermo, and we don't really treat it. There's a class for that. It's kinetics. You take it in the fall, right? So we'll be specific. Kinetics is not described. There's no time in thermo, at least in equilibrium thermo when you first see it, like in 020. So we will never do this to you. Never going to do that. We're never going to take any time derivatives. We're never going to calculate rates. We only calculate what you get at the end of a process if you wait sufficiently long. Right? What is sufficient? Don't know. Okay. This is one way to think about it. Thermo describes the why and only hints at the how. I find this an interesting way to remember what thermo does and what it doesn't. So for instance, when we ruptured the hot pack or we ruptured the cold pack, we could understand those spontaneous reactions. We understood why. One of them was driven by entropy, the other was driven by energy. That was the why. But the how, we didn't talk about it. In fact, somebody thankfully asked me a question how that worked, what was actually going on inside the bag. It had to do with two different bags and the surface preparation and supersaturation. Thermo doesn't really treat the how, it just gives you some ideas. So it's a starting point for understanding the how, but it does tell you the why. All right, what about the uses of thermodynamics? You're here. You're here because thermo is useful. It's really useful. Whether you become scientists or engineers, it's really useful, and that's why we make you take it, right? So how's it useful? How do we use it, right? We use it to predict and control matter. And we use it to transfer knowledge. Again, an example being phase diagrams, which are great summaries of knowledge. All right, so let me give you an example. Let's have a temperature axis here. This is temperature in degrees C. And we're going to study water at 1 atmosphere of pressure. So it's one-dimensional system here, temperature. And here it is, and here it is boiling. Right, okay, so what is the freezing point of water? Somebody, you know this, right? What's the freezing point of water in C?
0 degrees Celsius.
0, right. I'm freezing right now in this basement in the woods in Vermont, so I'm freezing. What about if we're here in the summer, right? Okay, it wouldn't be boiling. But what is the boiling point of water in degrees C? 100. Someone put the chat. Well, I don't really monitor the chat, not because I'm anti-chat. It's just one too many screen cluttering up my thing. So next time, please use the mic. But yeah, it's 100. Thanks. So okay, here's a question. How did you know that? Okay. Anyone who just did a quantum chemical calculation from first principles, I want you to raise your hand. Right? No, nobody did that. In fact, if you did, you'd probably be writing a paper right now, because that's still a very, very, very hard calculation. In fact, I've never seen it, an accurate prediction of the freezing point of a liquid from first principles using theory. So how did you know that?
These are material properties of water.
These are the material properties of water. You know that because you know that. You know that because the data that's out there, you have access to. Materials have properties, and some of these are so commonplace that you know them without having ever taken a class, right? So these are observations. These are observations. These are two of the huge number of observations on materials that mankind has taken, right, over millennia. Thermo gives you a framework for ingesting those observations and using them to make predictions about states that you have never seen before. So this is the way to think about it. Empirical observations right, so it's a bunch of observations, observation 1, observation 2, observation 3, right? All these little pieces of data, right? They get fed into something called the laws of thermodynamics, right? This is the conceptual framework. And then from these observations and the laws of thermodynamics, you can deduce predictions, or what I like to call it, decisions. Because when we're scientists, we talk about hypotheses and predictions. But when we're engineers, we have to make a decision, right? What temperature will I run this furnace? How high can this autoclave run without ruining my product, right? What's the maximum temperature that this product can see during shipping, right? And you don't have time to run a million experiments. So you need a deductive framework to make decisions, and that's what thermo gives you. How do we store observations? We store them in databases. So as you'll see, starting in the first preset, thermo concerns itself very much with the maintenance of databases. Without materials data, these laws of thermo are just text on a page. They're utterly useless. You need the data fed into the deductive framework to make decisions. So the databases have huge economic value. When you download the student version of ThermoCalc, they're giving you a very minimal set of databases. First of all, you'd have to pay a fair amount to get a larger set. But if you want to get the real stuff, these are trade secrets. So companies like Alcoa, they guard their thermodynamic databases the way a company like Intel guards its lithography masks, right? It's like the key to the entire operation. So the economic value of data is huge in thermo and in material science more generally. Now, fortunately, we don't need to sit down with our pen and paper and figure out what the law of thermodynamics predict. Every time we have software for that. So databases fed into software allows you to make predictions and helps you make decisions in a reasonable time frame. That's how you'll use thermo in the real world. This is how you use thermo in the real world. Okay. So. All right, next topic, systems in thermodynamics. All right. Systems are characterized by temperature, pressure, volume, and composition. Also, boundaries. Okay, so here's an example. Here is a balloon. Here's a boundary. This is in, and this is out. All right, so let's say we want to calculate some properties of the gas inside of this balloon. What should we take as the boundary of our system? It's kind of painfully obvious, right? You take the plastic, right? You take the actual balloon that you choose that as your boundary. That makes sense. It's kind of obvious, but it's good to start from an obvious example. Why do you choose the physical balloon as the boundary of your system to analyze the gas inside? Why not just choose an arbitrary volume? Why not say, no, I'm going to choose as my system the lower half of the balloon. And this is an imaginary line or surface separating the two parts of the balloon. Why not choose this lower volume to analyze?
Because there's nothing separating it from the upper volume of gas?
There's nothing separating it, and so as a result, particles can move between the lower volume and the upper volume. So if I choose the whole balloon, I get to use conservation of particle number. That's convenient. Right? If I now treat these as two subsystems, system A and system B, now I need to keep track of how they exchange particles. It's more work. We get the same answer if you do it right, but it's more work. So this is, again, a painfully obvious example, but starting as soon as this preset, we hope to make it give you some slightly less obvious examples, which is how you choose boundaries. You choose boundaries chosen out of convenience. Right? You choose a boundary when you analyze a system to make your life easier. It depends on what questions you're asking. So I believe on problem 1 on the PSET, we ask you to run through some of these mental exercises for different examples. Right, okay, boundaries chosen out of convenience. So let's do an example. Example, adding sugar to a glass of water. And stirring. So let's see. Let's draw a beaker. And there's water. Good. And here's sugar. There's sugar, and the sugar gets added. And I'm going to have a stir bar. I have to stir. So I have a stir bar, a little swizzle stick or something. And stirring that around so it's moving. This is water. All right. Let's talk about the system. First, I'm going to write down a list of all the things in this picture. So the things are water, sugar, the glass, the atmosphere. I didn't really draw it, but it's there. And the stir stick and the stir bar. Okay. I want to get an answer like, how sweet will the water become? Right, that's the answer I need. What system should I analyze? What should be in the system and what should not be in the system? So would somebody say, should the water be in the system?
Yes, because it's one of the main components of the mixture.
Yeah, okay, so we're going to choose the water. And the sugar, I will say also, is one of the main components of the mixture. So, okay, that's good. What about the glass? Should that be part of the system?
No.
Probably not. Unless we expect some kind of maybe reaction with the glass, but it's sugar water. It's not going to etch the glass, right? If this were hydrogen fluoride solution, it would etch the glass. We'd have to include the glass, but we're not going to include the glass. The atmosphere, do we have to include that?
No, because it's not changing.
Yeah, if this is just something you're doing in your kitchen, probably not. If you're running a factory making sugar water, like a simple syrup or something, you probably want to include the atmosphere because you want really good process control. And the humidity in the atmosphere might make a difference. That's an example. Or if you're a monk, right, brewing a farmhouse ale, and we know that the stuff in the air from the surrounding farms makes it into the beer and helps, change. So there are examples where you do want to include the atmosphere in the system, but here not. And the stir bar, not, right? The stir bar has a function, but it's not going to be a part of the thermodynamic system. What about the boundaries? All right. These are the types of boundaries. And before we go through these, this is as good a time as any to remind you that the associated reading is every bit as much a part of the course as the lectures. So if you keep up with the reading and do the associated reading before lecture, you'll get a lot more out of the entire experience. So thank you for keeping up with the reading. All right, boundaries. Open or closed? Somebody please tell me, is this an open or closed system? Which would you choose? And why? And what does that mean, open or closed? Somebody.
I would say it was closed, Because nothing is leaving the system, like there's no evaporation happening or particles leaving.
Good, okay. That's what I would choose too. Closed means no loss of particles or no gain of particles, right? Particle number remains the same. So the example given there was that if you included evaporation, loss of water, it would be an open system, right? You'd have to include the atmosphere in your system, and if you're doing a crystal growth experiment, right, you slowly let the water evaporate, the supernatant, right, then it's an open system, right? But we're doing this quickly, and we're not going to wait for water to evaporate. So close. Thank you. All right, rigid or not rigid?
Maybe not rigid, since the top is like, not like a hard solid surface.
Okay, good. So the top, not rigid. That's what I would choose too. Let's talk a little bit more about what that means. It means that the volume can change. The volume is free to change, right? That's what was said there. The top is not a hard surface. So we assume that the walls of the glass are rigid. They're not going to change. But the top surface is what's called a free surface. It can exchange volume with the atmosphere. And the ability to exchange volume, that's the mechanism by which two systems arrive at the same pressure. So this notion of pressure regulation, temperature regulation, becomes very important in thermo. Non-rigid systems are pressure regulated because they can exchange volume with the atmosphere. If there's a fluctuation in atmospheric pressure, that same temperature, that same pressure fluctuation will be felt by the water bath, for instance. As opposed to a rigid system can build pressure, right? You can have a bomb or a high pressure vessel that's a different pressure from the outside. Why? Because it's fixed volume, rigid. All right, good. And finally, adiabatic or diathermal? All right, so the non-rigid meant that you're going to be at atmospheric pressure throughout. In my view, the Zoom video camera, webcam review is blocking this text right here. Is it blocking this text in anyone else's view?
No.
Okay, good, thanks. All right, so what about adiabatic or diathermal? Is this adiabatic or is it diathermal? The boundaries, the adiabatic or diathermal. So adiabatic means a process or a boundary that does not allow heating. So a thermally insulating boundary. And diathermal is the opposite. Diathermal is a process or a boundary that allows heating, allows heat to flow, allows heat exchange.
So it'd be diathermal?
It'd be diathermal, right? So in the same way that the free surface allows the atmosphere to regulate the pressure in the water, keeping it at atmospheric pressure throughout, the diathermal boundaries, and glass might be a little slow thermal transport, but definitely you have a very fast thermal transport there at the free surface. This is going to keep, I'm going to keep temperature of the room, let's just see temperature of the room throughout. So the diathermal boundary regulates the temperature. The non-rigid boundary regulates the pressure. Okay. I'm taking my time here and intentionally introducing a bunch of new terms, or if they're not new terms, the meaning of all these terms is very specific in thermo. So the idea of regulation, the idea of choosing boundaries. Okay. So you'll do some examples like this in the PSET. All right, let's talk about types of systems, classifying systems. Classifications. All right, so this is just getting some essentials out of the way here. Unary, one component. All right, so an example of a component would be water. Okay, so here's an example. A unary system has one component, one molecular component. A multi-component system has more than one. So for example, the binary system of water and sugar. I've got hydrogen, oxygen, and carbon here. How come it's not 3 component? Anybody?
Because at no point are we discussing like the separation of those components.
That's right. At no point are we breaking bonds when reforming molecules. This is remaining water throughout. This is remaining sucrose throughout, right? This is not a digestive system, right? You break down the sugar. This is not an electrochemical water splitting system where you might be using some source of energy to electrochemically generate hydrogen gas from water, right? So that's good. So your choice of unary or multi-component, there can be more than one answer. And the same molecular components can be analyzed as unary or a multi-component system depending on the situation, right? So again, you make these decisions out of convenience because you understand the process that you're engineering, that you're designing, right? Okay, good. So that's unary versus multi-component. And this kind of gets sometimes you get a little bit easy to get tripped up there. All right, 2 different types of classification: homogeneous versus heterogeneous. So homogeneous means one phase. So, for example, sodium acetate, sodium the sodium acetate solution, right? That was the supersaturated sodium acetate solution was a starting point for the instant hot pack. Okay, sodium acetate solution. What about heterogeneous, more than one phase? Right, solution plus solid sodium acetate. Okay, so that's requires, I think, a little bit less description. What about closed versus open? All right, this we've already discussed. No mass exchange with surroundings. Versus can exchange mass with surroundings. Okay. So those are some basic and important classifications. Okay, next category. We're going through the sort of necessary stuff here to get started on real thermal problems. State functions. Or if you like, variables. We'll use these interchangeably. State functions and state variables. So these characterize a system. They are independent of history. This is a really subtle point. This will trip you up. It trips me up. Seems obvious, right? The fact that you could characterize a system with variables which are independent of the history of that system is very non-obvious. That was a major intellectual accomplishment. It shouldn't sit easily with you. That takes some getting used to. You shouldn't trust me on this yet. Okay, common state functions. Found in O2O. All right, so would somebody like to volunteer a state function? A common state function you might find in thermo?
Temperature.
Yeah, temp. So that's a state function. We'll use T. Volume. We'll use V. Pressure. We'll use P. Any others?
Enthalpy.
Enthalpy, okay, that's a state function. What about one that's not so specific to thermo? Are there others that are more colloquial?
Concentration.
Concentration, I'll say composition, yeah. Composition. And we'll use atomic percent very often in this class. Yeah. What about mole number? Right. Total system size, like that. And then there's enthalpy, and then there are others which are more specific to thermodynamics. There's entropy, there's Gibbs free energy, and there's Helmholtz free energy. If we were course 2, if we were mechanical engineers, we would be spending a lot more time on Helmholtz free energy and enthalpy. If we were physicists, we'd be spending a lot more time on Helmholtz free energy and energy, which we're going to use U for internal energy. But as material scientists, we spend most of our time on Gibbs free energy and enthalpy for reasons that we'll discuss at length in a couple of lectures. Okay, but there are more. There are more, like magnetization. Right? That's one we don't. Electric polarization. There are many. Right. Okay, so we have state functions. We have state variables. We also have equations of state. So an equation of state in general is some state function x equals a function of other state functions y1, y2, y3. Right. And in this formalism, that's a state function, and these are state variables. But I'm going to use this interchangeably, state functions, state variables. All right, so you all know one state function. What's a state function? Everybody knows. It's even on the t-shirts. When I do this lecture in person, I wear my MIT t-shirt with the state function on it.
Be Pivnert.
Yeah, Pivnert, right? P V equals N R T, right? Okay, so that's a state function. That's a state function for an ideal gas. This is true always for an ideal gas at equilibrium. That's pretty cool, and you can do a lot with that. But before we do a lot with that, I want to warn you, this is the exception rather than the rule. For almost every system, every material which you'll use in your careers, we do not have a state function like this. Maybe we have some that are empirically determined. You might find some magnetic systems for which state functions have been exactly derived from fundamental principles like this one. But this is the exception rather than the rule. Usually, you can't write down a closed form like this. Usually, you have to deal with much more complicated data resources. Right. Something on units here. Try to sneak this in. R equals PV over NT. What are the units of that? Pressure is pascals. Volume is meters cubed. These really look like pascals. Mole is unitless, just a number. And temperature is Kelvin. In fundamental SI units, a Pascal is a Newton per meter squared. Force over area, right? That's pressure. We have a meter cubed, and we have a Kelvin. So then you get Newton meter by Kelvin. And what's a force displaced over a meter? Newton meter?
A joule.
Oh,
Joule. Joule Kelvin. So R equals 8.314 joules per Kelvin. It's a handy thing to remember. We're going to be sticklers for units in this class. Equations of state. All right, more things. Thermodynamic properties. All right, so at the very beginning, I told you that states of matter had certain responses when you squeezed them or you added stuff or you heated them, right? And these are going to be described by thermodynamic response functions. So that response function term sounds kind of fancy. Don't let it scare you. It describes how a system responds to something. So if someone screams, you cover your ears. That's your response function. So some common response functions that we use in thermo are compressibility, isothermal compressibility, right, at fixed temperature. And of course, this is the same as d log v dp. So you see this a lot. Okay. The only real prerequisite for thermo is multivariable calculus. And I think the first time I learned thermo, and probably the second time even, and I didn't appreciate just how much it relies on multivariable calculus. So just know that now, and so that you're not surprised later. All right, thermal expansion. It's another common one. Alpha equals, again, we're going to make this volume independent. And we're going to do that at fixed pressure. Okay. And there are others, but these are, the easiest ones to write down, and giving you an idea of the sorts of properties that we're going to calculate in thermo. So let's consider ideal gas compression at fixed temp. Volume initial at pressure initial going to volume final at pressure final. All right, so compressibility equals minus 1 over V dV dP at fixed temperature. And for an ideal gas, this is very, very simple. This is minus 1 over V d dP at fixed temperature nRT over P. This equals nRT over Vp 1 over P equals 1 over P. This is really simple for an ideal gas, and only for an ideal gas. So the final volume after compression is going to be the initial volume plus the change. So that's like second fundamental theorem of calculus. So we're going to plug in. What's the integrand? it's minus V beta. And you continue to plug in. This is volume initial minus final dP and nRT over P, 1 over P, equals V initial minus nRT P initial plus nRT P final, which of course just equals volume final. So this calculation is really trivial for an ideal gas. You get exactly what you think you would get. The reason why I took the time to do it is to show you the sort of manipulations that you'll need to do later on for non-ideal gases. So thinking about this, you got to put your multivariable calculus hat on. Of course, for an ideal gas, we get this 1 over x, these relationships. P initial, V initial, P final, V final. And this curve is an isotherm. So we'll come back to these when we do heat engines and the Carnot cycle at lecture 4. Okay. We're almost done. Let's see. Two last points here. Intensive versus extensive properties. All right, intensive properties can be defined and measured at any point within a system. Would somebody like to volunteer an example of an intensive property?
Temperature.
Yeah, temp. Right. When they take your body temperature, they assume that you have one body temperature, and they can take it, there's different places, right? They can stick the thermometer, but you should get the same number. Density. Right, you can locally define density and you can measure it locally. Composition for a uniform system, composition. Pressure. And there are more. Okay, extensive. Extensive properties depend on the extent of a system, and they scale with system size. All right, so some examples here would be energy, volume, mass, entropy, and so forth. All right, the doctor can take your temperature at several different places, but to weigh you, your whole body has to be on the scale, right? They can't weigh you just by weighing your arm. Simple thing. So extensive, you need to know the extent. Intensive, it can be defined and measured at any point inside or within a system. Easy way to remember that. All right, we're going to end today with definition of the phases, a phase of matter. All right, so I'm going to define a phase the following way. Phase is a region within which all intensive properties are uniform. All intensive properties are uniform. That's a phase of matter. Okay, so for example, solid sucrose. All right, some things we've seen here, water. All right, simple syrup. Brass. All right, some examples. On length scales. It's an important caveat, right? If I zoom down to atomic length scales, right, I might say this isn't uniform, right? I've got different metal elements depending on where I'm looking. So this has to be on length scales larger than molecular length scales. All right. And phase boundaries, which of course are a really important topic in thermo and material science, are classified similarly to system boundaries. Right. So when we have a two-phase system, for example, sugar and water, we have some sugar. And it's in water. We have a sugar-water system. Right, and we're going to think about this boundary, right, in the same way that we classify system boundaries. And so that's an open boundary, right, because sugar molecules can go across the boundary into the water. And similarly, sugar molecules can come out of solution and go back into the solid. Right, this is a boundary that exchanges volume, it exchanges heat energy, and it exchanges mass. Okay. Good. So that's all I had prepared for today. It is 10:54, almost perfect. Thanks for joining. As usual, I'll hang out for till at least 11 if folks want to talk or ask any questions. Otherwise, I'll see you Monday.